Okay, now we are at part 8 of the series on making estimates of systems. And in this one, we're going to extrapolate densities, residuals, and demands through the system curve. It's a new concept that we have yet to explore. Like all these videos, these are for entertainment purposes only. They're back of the envelope calculations to uh, help you use your time wisely in prioritizing work. There are no means a method to evaluate a sprinkler system or make changes of a system. The only time you should be making changes to a system is after a hydraulic calculations has been calculated and good water supply test is available. We touched on this briefly, but I need to follow up on it. And that's flow through an orifice. And what we have is a series of equations here. The first equation is a theoretical flow through an orifice of Q equals AV. And I'm not going to go through this in a whole lot of detail, but know that this equation exists. You can easily find it online. And through a series of manipulations, we can get it to a form that looks like Q equals 29.84 CD squared, square root of P. And that's the flow, and the P is obviously pressure. This is a actual um, equation for flow as opposed to the theoretical of Q equals AV. As you'll notice, there's a C in there. And that C accommodates friction, turbulence, and constriction of streams. So that C will change depending on the configuration of the orifice. And it's more likely to be seen in this form of Q equals K square root of P. We're going to be using Q equals K square root of P. And again, Q is the flow in GPM and P is the pressure in PSI. And that K represents that 29.84 CD squared. Let's see how it gets used in some upcoming graphical work here. What we've been introduced to so far in terms of graphing has been the supply curve. That's the water supply with the static and residual and flow. And then last video, I presented the hose stream allowances where we deducted either a 250 or 500 GPM uh, hose stream allowance from the water supply, resulting in a smaller water supply. Now I want to introduce another concept, and that's the system curve. And in this particular case, I've got a sprinkler density of 0.3 over 2000, and it flowed 650 GPM at 70 to achieve that 0.3 over 2000. So just to kind of go through some of the terminology, the 650 GPM is demand, the 70 PSI is the residual, and one other wrinkle in this will be that the sprinkler system is 20 feet off the ground. And so if we look at how this is graphed, again, it's graphed on semi-log 1.85 paper, and you can see that I've got a dot at 650 at 70 PSI. And then you'll see if you go to the far left that the curve does not start at 0, but it starts at a number higher than 0. As a matter of fact, it starts at 8.66. And the reason for that is that it's taking the elevation of 20 feet times 0.433 to come up with a pressure loss due to elevation. So that loss is linear as opposed to the frictional losses, which are to the 1.85 power. And that's why you don't start the curve at the 0 mark, but rather at the mark of the elevation of the sprinklers above the water supply. Couple of things. So it's an interesting point about this curve is that this curve is valid for um, any point along the line is valid for the sprinkler system. there's a couple of things to keep in mind here. The this this sprinkler system curve is only valid for 2,000 square feet. What we're saying is that we have reduced the sprinkler system to a Q equals K square root of P. We've reduced um, the entire system to just one large K factor. When you get a sprinkler head, for instance, you'll notice that there's a K factor associated with it, 5.6, 25.2, etc. Well, we can reduce the configuration of piping and the outflow through sprinkler heads to a K factor as well. And that's what we're doing with this particular chart, this graph. We're reducing the entire configuration of the sprinkler system to a K factor. And what we're able to do is slide up and down on that curve using that K factor. There's a couple of things to keep in mind that are important. This graph, this system curve is only valid for 2,000 square feet of operation. It's only valid for the operation of those heads that are flowing. If I flow an additional 2 or 3 heads more, that curve is not valid. It's only valid for 2,000 square feet. And it's really best if all the sprinklers are at the same elevation. If, for instance, we have sprinklers at different elevation, it throws a problem into it, because now we're not only dealing with friction loss, but we're dealing with elevation losses as well. So it's imperative that if you are using the extrapolation of the system curve, that it always have the same design area with the same number of heads flowing, two, that that the sprinkler heads all be at the same elevation. So how do we use that graph to determine demand and residual for a different density? And it's actually very straightforward. There's a linear relationship between water supply, between the demand and the density, and I've listed it below here. It's 0.3, which is the initial density over the desired density of 0.37. And that 0.3, if you remember, corresponds to a demand of 650, but we don't know what the demand would be for 0.37. So when we cross multiply, you have 240.5 equals 0.3x, and solving for x, we end up with 801. And then we'll show on the next graph that that the demand is for that density of 0.37 over 2,000 is 801, and we'll be able to pull the residual pressure right from the graph. And here's that same system curve, starting at 9 psi. There's our 650 at 70.3 over 2,000 point, and now we have that new point of 0.37 over 2,000, and we're going to determine the demand and residual based on that curve. And it's, as you can see, if you just go down to the point, it says 800 at that point, and if you go across to the left, it's 100 psi. So very simply, we have determined the demand and residual based on a simple graphing of the system. You could also do this through calculation. I'm not going to bother with that because this is so simple. You can go to Harold Wass's book that I referenced earlier, Sprinkler Hydraulics, and they've got a series of calculations and equations that will help you do that. But this is so simple that you really don't need to go through that exercise. So basically, we've been able to slide up and down this system curve to extrapolate different densities, demand, and residuals based on a single point. And remember, of course, that the is only based on 2,000 square feet. Again, it can be based on any square feet. I could have a 4,000 square foot area, but that would be a different system curve. It would look different. One other point I do want to make is that the equation of Q equals K square root of P can also be turned into K equals Q over square root of P. So this K um, does vary slightly based on, and so you'll see it's to the square root of P, but it can also be, there's a little bit of leeway in there, and it can be to the up to the 0.54 power, and it's really based on, so the K does vary slightly with pressure, but for the sake of this discussion and the way people handle this situation, they ignore the slight discrepancies in K factor when using this extrapolating method, and they use it to the square root. I know Factory Mutual years ago delineated densities less than 2 and greater than 2 with different Ks of between that K, P to the 1/2 to P to the 0.54 power. But just know that if you just stick to the way I'm explaining it to you, you're pretty much standing on solid ground. We have our system curve, the 0.3 over 2,650 at 70. And let's just add a water supply to it and see what that does. And in this case, I've selected a water supply, a pretty strong water supply of 120 psi static, flowing 900 at 70 psi. And that's graphed there as well. And so as you can see, anything above the water supply, any point above the water supply is incapable of meeting the demand. So for instance, I have a demand for 0.37 over 2,000, I need 800 at 100, and it looks like I have 800 at about 80. So I have insufficient pressure to meet the demand and residual for the 0.37 over 2,000. But as you can see, I have 20 plus PSI to spare when I am looking at a 0.3 over 2,000 system at 650 at 70 PSI. I said in the last presentation that I wouldn't add the hose stream into it, but just for sake of discussion, I'll do that just so you can see what happens. In this case, we've got the system curve, we've got the water supply, and I pulled out a 250 outside hose allowance. Generally would have been 500, but just to kind of make this thing clean, I just had a 250 reduction. And as you can see, now, of course, the 0.37 is deficient by a significant amount, and the demand and residual for the 0.3 over 2,000 sits right on the new water supply with the outside hose in place. The sprinkler system would still be adequate. Well, that's I tried to do this as quickly as I could. My goal was to complete 12 of these videos for the year. I have one more, kind of a nice one, I think, to finish this up. I can't tell you how much I've enjoyed doing these. We haven't really caught on much, but it's been a blast for me to do them. I don't know if I'll continue doing these. As much fun as they are to do. This was really a placeholder. I expected to write a nonfiction piece about a certain fire over the winter, and in November of last year, when I went to start to do my research, I found that it had been so well covered that there was no sense in me going over it. I now have the topic in place. I'll be writing starting probably in November of next year, of this year. And I don't know if I'll do this. I also, over this winter, did complete a science fiction novel. So it took me a little over 90 days to write a science fiction novel. I'm editing it right now. So it'll be called What Have We Done? So if you get a chance to see that, hopefully I will be back. I have no idea what I'll do with this channel. I've really enjoyed doing these, although not many people have viewed them. There's some awful good information in there. Hopefully we'll meet again in the future. If not, keep an eye out for my name. In a year or two, I should have a pretty good nonfiction book on some historical fires. So more to follow. Hope all is well. Bye.